Okay, so continuing with the wavy wall problem. So we came up with an expression for the surface pressure coefficient, right? So so wall pressure coefficient, it looked like this, right? So this was the expression, and then also we looked at how this really is acting on the surface, and we saw that you know let's look at the equation of the surface. That the surface equation, the contour equation rather, it was given as the wall contour equation was given as. So you can see that both these quantities, they basically are functions, are cosine functions, right? However, this is at 180 degrees phase lag because of this negative sign, as a result of which we saw that there was no horizontal component of this pressure, as a result of which there was no drag. So which was the commonly known D'Alembert the paradox. Okay, so now let us just look at this a little more closely and see what exactly this means. Okay, or if any other information we can draw from this equation out here. Okay, now let us see. Say for a certain value of m infinity, right? So say as y say is very, very large. Okay, so we are basically looking at a distance which is very, very far away from the wall itself. So y is very, very large. Then what happens to Cp, right? So if y is very, very large, then essentially right, tends to 0. Now what this essentially means that as we basically move farther away from the wall, right, the disturbances die out, right? So which kind of makes sense, right? So the more we get away, the slowly, so basically we can say that as y increases, the pressure coefficient decreases, and which in turn would also mean that the velocity, the perturbation. Okay, now let's look at the, say, the perturbation velocity potential, right? For example, if you look at this, now the perturbation potential, okay, now that is proportional to essentially and exponential So if you look at this as well, so when y increases, basically this tends to 0, which means that, so if you look at this, so which means that the perturbation dies out, or the perturbation velocities die out, which essentially means that the disturbances die out as we move farther and farther away from the wall. Okay, that's one inference which we get from here. Now another is that in here we are really looking at, so let's get rid of this. Okay, so now here we're looking at subsonic, right? So we are looking at the analysis that we've done so far is for subsonic flows, right? So therefore in here, now look at this. Now if m infinity increases within the subsonic flow, if m infinity, if the Mach number increases, then what happens, right? If Mach number increases, look at this term, look at the pressure coefficient here. If Mach number increases, then this decreases. So this basically increases. Okay, this increases. Now let us say look at also look at this, and now at the same time let us also say phi p. Let us look at also this. This is also proportional to this, right? Now see if Mach number increases, so this term basically decreases, so this term increases. Now this has to correspondingly increase. This has to correspond, this term actually increases, so this term has to correspondingly decrease to keep the proportionality correct. So similarly you have the same thing here. The Cp is also similarly it's a function of it is also proportional to pretty much the same thing, right? So therefore if Mach number is increasing, so if this has to decrease, right? So now in here, so therefore if Mach number is increasing, right, so this term decreases, so this has to correspondingly increase, right? So if Mach number increases essentially, so y also increases, which means what? What does that physically mean? Okay, let's look at this. So we have, so essentially what we're saying is if you look at the perturbation potential here, okay, so if the Mach number increases, the y also increases. So this is the relation of the perturbation potential with y, and again this is also hence the relationship of the pressure coefficient as well. Now if you look at this, now say this is our wavy wall, right? So this is our wavy wall, right? Now say this is at a Mach, say this is at flow is happening here, say at a Mach of say 0.1, right? Say this is happening at 0.1, okay? And another case is that we have the same wall essentially, and this here, so this says 0.9, okay? This is say 0.9. Now what we said is that if Mach increases, y has to increase. So Mach has increased from 0.1 to 0.9. Now the y has to increase. What does that mean? What that means is that in this particular case, you have the disturbance. So say it moves like that, moves like that, moves like that, moves like that, and so on and so forth, okay? So it goes up to a certain, and after that it dies down. So therefore you have a certain, okay, so you have a certain y distance over here, okay? So you have a certain y distance over here. Okay, now in here, however, let us see. Now we are saying that as Mach increases, y also increases. What this means is that right, and therefore so essentially what we're saying is that as for subsonic flows, right, as the Mach number increases, so the disturbance also travels to a farther distance, right? The disturbance also moves, you can see here, it moves to a farther distance in y away from the wall. So that's what that means. Okay, so pretty much having done this now, let us go and look at the same problem, right, for a supersonic case, okay, using the same linearized theories, okay, and see what we can infer from there and what sort of equations we will get, right, and how do we go about solving those, and then we'll sort of sum it up. Okay, all right, so here we go. So we will start with the perturbed velocity potential equation. So the perturbed velocity potential equation was, this is what we had done. Right. So this is what we had originally done for the subsonic case. Okay. So now let us do this for a supersonic case. So where we will write this equation as, say, let us write it like this way. Okay. Right. Now, if you write it this way, then let us look at the 2D picture of this. So, which means that we're basically going to look at this, right. So, this is our equation. This is the 2D picture. Okay. So, if we look at this, so or we can write this as right. So, if we have this now, if you, I'm hoping that you're recognizing this equation is a typical Wavy equation, and mathematically this has a set for solution to this, right. So, therefore, we can write this solution to this in this form, right. So, we will take two arbitrary functions and say phi p here, okay, which is a function of x and y, is therefore equal to, say, right, right. So, this is our typical solution for an equation like this, right. So, now we use a method of separation of variables for the subsonic case. Now, in this case, however, we this is in this the Wavy equation. So, we have a solution which will look like this. Now, let us sort of again go ahead and find an expression for this. Okay. Now, to do that, so let us say we will set g is equal to 0. In here, let us say g is equal to 0. So, to find a solution for that, so let's say we will say g is equal to 0, right. So, that makes my right. So, this is my velocity potential equation now. So, therefore, right. So, del phi p del y is let us call this one. Okay. So, this is my del phi del y, okay, or v dash essentially, at the wall. Okay, so now so this is okay. This is not at the wall, so this is at the wall. So basically, essentially, this will go to 0. Okay, you're considering small perturbation theory. Okay, so this is del phi del y. Now, as we learned from our last exercise, so now del phi del y, right? This at the wall, okay, this at the wall is essentially the velocity so this is what we have derived yesterday as well, but if you just look at this expression, so the velocity, the perturbation velocity component at the wall is essentially the free stream component in the direction of the wall. Okay, so this is the slope of the wall. Okay, so this is what we've done earlier, and we have an expression for this dy by dx at the wall, which is what we get by differentiating the equation that we had for the wall, which was yw, right? So therefore let us just do that here. So like we said, now at the wall we will set now at the wall this y, considering small perturbation theory, right? So if we do that, so therefore let us equate these two here. So what we then get is this. Right, is equal to, and the slope was given as okay. So this is what we get. So here therefore we can get our f dash x. So let us get our f dash x, right? So which is equal to okay. So this is my f dash x from here. So this is what I get. Now, so let us sort of so let's say we will integrate this. Okay, let us integrate this. So let's see what we get. Okay, so f dash x is this. Now if I integrate that, right, if I integrate it, so what I get is fx, okay, fx is essentially okay, okay, so if I integrate this plus a constant, okay, so therefore this or essentially fx is equal to right. Now this fx is essentially at the wall. isn't it? We derived all of this essentially at the wall. So Fx at the wall looks like this. Now therefore, now if instead of, now we know that instead of any arbitrary position in the flow field, right? So that argument here was x minus this. So instead of x being just x, so let's say for any arbitrary x here, so if right. So if I have this, so therefore then this equation for any position in the flow field will look like okay. X is x okay, this okay, and essentially what this is equal to our perturbation potential. Okay, so therefore now this is what it looks like. Okay, so let's box this. Okay, and let's call this as say 2. Okay, now that we have done this, so basically we found a found an expression for the velocity potential here, and of course you also, if you will remember that if we took the if you take 0, if you take g to be equal to 0, then what this results in is essentially right running characteristics, right? And then if we take f to be 0, then what we get is left running characteristics. So we've sort of done that earlier. So now having got an expression for this velocity, the perturbation velocity potential, what we need now is the coefficient of pressure, right? Surface pressure coefficient. So let's see what we will do, how we will go about that. Okay. Okay, now what we learned from last time is that the Cp, right, Cp at the wall is equal to this. Okay, Cp at the wall depended on the u component of the perturbation velocity, right? So if I have to do that, so let us say we will try to find expression for this using the perturbation potential, which expression for the perturbation potential which we have just derived, right? So if I were to do that, so let us say, let me write that again here. Okay, so phi p essentially now is equal to okay, so let us do this, right? So this is essentially u dash, isn't it? This is essentially our u dash. So del phi p del x, now this is a u dash. What do we get here? So what we get is Okay. Right. So if I'm just taking derivatives of phi p with x, so what we get out here is this 2 pi by L comes from here, and the cos, the derivative of cos is sine, so this is what we get, right? So this is our u dash, right? Oh, okay. So we took a derivative, so we get a negative sign here because of this sign. Right. So therefore, the what we get over here, yes. So let us say, so these signs essentially cancel out. So this is what we get. Right. This is what we get. Now again, now at the wall. Okay, at the wall, taking small perturbation theory. So again, y will tend to 0, right? So therefore, at the wall, what we get is okay. Okay, so this is what we get at the wall. So therefore, our CP, at the wall, surface pressure coefficient, right, which is the CP at the wall, therefore becomes, it is minus 2 u dash by V infinity, right. This is our expression for this. So what we get from here is this. So in here, therefore, that becomes right into right. So this is our expression for the wall pressure coefficient, and this is it. Now let us try and understand this a little more. So like we did for the subsonic case, let us try and understand this a little more, what sort of this means. Now as you can see that the wall, okay, let us just sort of point out a few things. The wall equation was, if you remember, the wall equation was okay, and the pressure coefficient equation here is this. The pressure coefficient equation here is this. Okay, so let us see what this means, and if we can get a little better understanding of this in here. Okay, now as we've done before, and as we just said, that taking either f as 0 or g is 0, we basically get left running or right running characteristics, right? So now, so if we do that, okay, now say if we take g is 0, if we take g is 0, so therefore lines of constant, if we take g as 0, so lines of constant phi, right? So lines of phi, constant phi, essentially, say they correspond to right? So they correspond to this, okay? Because phi p is a function of, is f of this, right? Which you've just done. So therefore, in this case, I can write the slope of each line, Okay, so dy by dx is this. Okay, so so essentially what we're saying is that so essentially we are going to get these lines which have a slope of, so dy by dx is essentially this, given by this. Okay, so let's say this is theta. So these are the right running characteristics we will get, and if you put f is equal to 0, we will get the left running characteristic. This is something that we did earlier on. Okay, so now having done this, now let's say then the Mach angle. Okay, so now this mu then, okay, is equal to this, right? Now and here, so now so if I do a little bit of math out here, then I can write this as okay. So now so therefore what we can say is that this is also dy by dx is also equal to, this is also equal to tan mu. So say let us keep the entire thing, box the entire thing, right? So dy by dx is given by this, okay, and this is also, the slope is also equal to the tan of the to the tangent of the Mach angle. Okay, now see at the wall, okay, now at the wall, okay, so theta is the tan theta, okay, so this is dy by dx at the wall, right? So this is tan theta is the physical slope, right? So tan theta at dy by dx is right, this is what we've done before, right, and taking small perturbation considerations, so which would mean that this is very small compared to v infinity. So what we get here is this, right? Let's say, so what we have out here is that phi now is equal to, we've taken g to be 0, right? So f of into this, right? So then this is the perturbation pollution. So the u dash is, right, which is equal to f dash, right? Now then v dash is equal to okay, and this is equal to right. So this, but f dash is also is equal to u dash, so therefore I can also write this as this, right? So therefore I can write that u dash is equal to now what we saw from here, okay, what we saw from here is that we can write at the wall tan theta is equal to this v dash here. So let us say now from here, let us say v dash we can write as v infinity tan theta. Now please try and understand this here, that this theta is the physical slope, right? So if you have, when we have the slope here, so when we have this actual wall over here, right? So then this is the actual slope, the physical slope of the wall that we are talking about. So that is the slope, right? And we have also said, so this is the dy by dx at the wall, and we equated that to the to this, which is essentially the angle which is made by the velocity components, right? And since the velocity vector is tangent to the wall itself, we are able to connect the physical slope to the direction of the velocity. Okay, and so therefore I can write that this, what we are basically trying to do here is that this is the perturbed velocity component in the y direction, and we are connecting that to the physical slope at the wall, right? So which is this. Okay, so now we've written here that the u component of the perturbed velocity is equal to this. Okay, and therefore we can also write this v dash, right? We can also write that as this, isn't it? Because because this can be written in terms of the physical slope of the wall, which is this, right? And considering that this is again small perturbation, so therefore we can say that this theta is really small. So then what we can write here is this, right? So what therefore we can write is this is equal to okay. So we can write this, okay, because for small perturbation, so this I will take as very small, and therefore I can write it as theta, right? If I do that, then what happens to my coefficient of pressure at the wall? Okay, so again, so therefore what happens to my coefficient of pressure then is this. Now coefficient of pressure is, right, this is my coefficient of pressure, and you can now I have an expression for u dash, however, in terms of the physical slope at the wall, right? So therefore I can write this as, and u dash we will incorporate this right. So what we get, Cp at the wall okay. So now this is what we get at the wall. Now this is very interesting, because what we see from here is that if, okay, let us sort of now take a look at this. Now say if this theta is positive, right, if this theta is positive, we get a positive CPW, and if this theta is negative, then we get a negative here, which means what? Which means that, okay, so let us draw a wall here. So say I have a positive like that, okay. So I have a positive, and then I have a negative, okay. So which means that as long as this is positive, right, so if this theta is positive, I have a positive Cp, okay. So let us do that right here. Let me draw the wall, right, okay, let me draw the wall, right, okay. So or say let's take a little bit of space here and do this. Okay, so let us do this over here. So if I look at this, okay, so say this is my Okay, this is the wall. This is my original. This is my physical wall. Okay. Okay, so if I look at that, now when I have, okay, now when I have, say, let us look at this part out here. Okay. And so on and so forth. Okay. Now this is a region, right? This is a region where theta is positive. So I have a positive CP. Okay. So I have a positive CP. Okay. And then I have what? And then if you look at this, theta is negative, CP is also negative. So if that is true, then this becomes negative here. So then CP I'm just using the conventional that. Okay. So this is what this means. Now I think by now you should be able to kind of figure out what this actually means from here, from these arrows, right? So these are basically showing the direction of the pressures. Now before we go back there, let us look at this here. So this is the other CP expression that we had got, right? So this, what this says, this varies as sine, right? And this varies as cos. So essentially what we will have from here, right? So is that, so if I were to do this, so let us say how should this look like? So if I were to do this, okay, so if I were to do this, so what this would look like is that okay, so that should be what we're getting from here, and hopefully you should be able to correlate between the two. Okay, so now let us go back to what we were doing earlier. Okay, now if you look at this over here, so now let us take, say, this and this velocity vectors. Sorry, the pressure vectors. If I look at this, I get this. Okay, and if I look at this, and I get this. Okay, so and let's take, say, another one. So let's take this, let's take this. Okay, so let's take this and let's take this. What do we see from here? What do we see from here? What we see from here, that unlike in the subsonic case, right, when this was symmetric, when the CP was symmetric, okay, so we had a CP distribution which was symmetric, as a result of which we did not have any drag, right? Unlike here in the supersonic case, you can see that the drag, the horizontal pressure components do not cancel each other. So we actually have a drag in this particular case. So the drag doesn't blow away, or it doesn't show no drag. Okay, so that is this is the prime difference between the subsonic case and the supersonic case. Okay, so we basically have an asymmetric distribution of pressure, as you can see, as a result of which, so if you just look at, say, this half lambda over here, so you have a positive pressure and negative pressure. And so as a result of which we do have a finite drag. Okay. Okay, so what we'll do now is kind of, so let's sort of take a minute and summarize the whole thing. Okay, so to do that, let's say, and also before we do that, where was our phi p? Okay, so we got an expression for phi p. Okay, so let us look at that. Okay, so let us say some of the things. So this was our subsonic, and this is our supersonic, right? So now we got an expression here for phi p, right, which was some of this sort. Okay, so which looked like this. Okay, exponential into sine. Okay, and for supersonic case we got a phi p, okay, which looks like this. Okay, so first off, the very first difference that you can see over here, that there is no exponential dependence of the perturbation potential on y, x or y there, on y actually, and for phi p there is for the subsonic case we do have an exponential dependence of the perturbation potential, right? And here, as we had seen, that as y tends to infinity, as we go farther away from the wall, this disappears, right? This disappears. Now if you look here, okay, if you look here, so this does not die out. Okay, in the supersonic case, however, we can't say the same thing. It's not like if you move away farther from the wall, the disturbance dies out. It doesn't. So essentially, like we said, we basically in here, so we have the disturbance which is propagated to infinity, right, on straight lines, okay, with a slope of 1 by this, okay, which is basically the right running or left running characteristics. Okay, so in here, okay, Cp at the wall, okay, Cp at the wall was this, right, and here of course, so here on the other hand, Cp at the wall, okay, this looked like right, and this was also equal to this. Okay, so this is how the Cp looked like. Okay, and we saw that this caused no drag, whereas this, because of its symmetry, whereas this did cause a drag. Okay, and so finally what we have here is an elliptic PDE, right, so which we solve using the method of separation of variables. That's what we did. Here on the other hand, right, we had an hyperbolic PDE, right, so for which basically is the wave equation, and that's how we also had solutions for that, and we came up with which eventually resulted in solutions which which were valid on right running and left running characteristics. Okay, so that should be all. Thank you.